Welcome to VMware Explore 2022 with the CTO Advisor Studio. Come on in and consume some content.
All right, this is the last video for VMware Explore 2022. Keith Townsend, your host. The CTO Advisor Studios. It has been an amazing show. We've talked everything from CXL with Stephen Foskett. We had the Great Beards on Storage. We've talked to Chris Wolf, Amanda Blevins, the America's CTO. We've had the technical and strategic conversations. Now this is more of a passion project for me. We're about to have one of my mentors from when he was hardcore unemployable. Now he's given up.
Now I'm employed.
Now he's
Nobody
just
understands
employed.
it.
It's been
Not
a
even
couple
me.
of years now. He works for Vast Data, but we're not talking about Vast Data directly. We're hijacking the show you gave to Ray, Gray Beards on Storage. This is the unofficial Gray Beards on Storage.
This is the
Howard.
other Graybeards on storage.
This is the other Gray Beards on Storage. I have with me Howard Marks, not that Howard Marks. Howard Marks, Deep Storage on Twitter. How's it going, Howard?
It's going great.
So, Howard, the Micron announced this super nerdy thing a while back ago. It's, they kind of scooped the industry with 232 layer NAND.
Yep.
And they made an absolute big deal of it. Matter of fact, I'm headed there next week to shoot some content with them. They're really excited about it. You know, I'm a cloud architect. I'm cloudy enterprise architecting thing,
Yep.
and I need people like you to tell me why 232 layer NAND is important.
Because stacking is how we make flash cheaper. So back in the day, in the 90s, the flash that was in an SSD had like a 49 nanometer diameter per cell.
That's huge.
And it got denser by shrinking the diameter.
Right.
And so we got down to about 12 nanometers.
Okay.
But at about 12 nanometers, there's only a handful of electrons in that cell. And the leakage that gets created when you erase starts to get so large you can't error correct it anymore. So you can't get smaller than that.
So let's talk about the layer of that manufacturing process versus the manufacturing process for CPUs. 12 nanometers for a CPU would be considered fat today.
Right.
12, 14 nanometers. Intel had a hard time going from 14 nanometers to 10, but the nature of a CPU and the nature of storing and erasing bits is different.
When we use those nanometer terms,
Right.
for anything but flash, we're talking about the size of the smallest thing that they can apply via lithography to the cell.
And we're talking about zeros and ones.
No. We're talking about the little copper wires that connect the transistors together.
Gotcha.
So when you say 7 nanometers, the little copper wire that connects the transistors together is 7 nanometers wide.
Okay.
The transistor is about 3 times that big. Flash cells have to be even bigger than that. So for a given node of lithography, the size of the cell in flash is still a multiple of that.
Gotcha.
So we're talking about dimensions of different things.
Okay.
But the point there was just, we had planar flash, which is how, DRAM and CPUs are made, where there's one transistor built up and then they're connected like a circuit board.
Right.
But when we got to the point where you couldn't make the cell smaller because it wouldn't be reliable as a charge trap anymore, we had to go find some other way to get more bits per square millimeter of silicon.
Gotcha.
And being a New Yorker, I understand completely, when you run out of land, you build up. And that's what the flash vendors did. So Samsung was the first. They found a way to build up to 16 layers, and layer in semiconductor means different things. In this case, layer means a whole cell.
Okay.
In the manufacturing process, that's made up of about 20 layers of resists that get applied in lithographed and such, but for this conversation, a layer is a bit.
Okay.
And the problem with stacking is the manufacturing process builds up layers of the various materials.
Yeah, literally as you're talking, I'm thinking about 3D printing.
It's actually, you drop a little bit of a liquid on the wafer, and it spins to get it completely even.
Okay, gotcha.
And then it gets exposed to light that causes some of that to stick, and then it gets washed, and the part that didn't stick gets washed off, and rinse repeat like 10 times to make a cell.
That sounds labor intensive.
All automated, all
right.
sealed.
But even with the machinery needed to do that repeatedly, consistently across millions.
The lithography machines are made by 2 vendors in the world, Zeiss and a Dutch company, ADML.
Okay.
If you want to order a lithography machine for 7 nanometer, that machine costs several $100 million and has a 2-year lead time.
Okay.
But most of the cost of a chip is the start, the wafer, getting it into the factory. The additional going, well, instead of doing this wash, apply, spin, light, repeat, 10 times, we do it 100 times. You've only raised the cost a couple of percent.
Okay.
So building high costs a little bit more than not building high, but most of the cost is in having the wafer, so it's cheaper to build high.
Gotcha. I never knew this stuff.
The problem is you do all of this apply, wash, release, then you have to etch little tiny holes perfectly straight through all those layers of silicon and silicon dioxide that you've laid down. And then you have to plate the inside of that hole with copper or gold to make it conductive. And the flash foundries keep learning how to get that little tiny hole perfectly straight longer and longer so they can stack higher and higher.
Okay, I really do get the skyscraper reference. Start out with a 4-story building, going from a 4-story building to a 100-story building.
It's actually very much Empire State Building, because each cell layer is a little bit shorter. It's a staircase. Because that way there's an opening to create a connection into each one.
Okay.
And so how deep the stacks are keeps getting higher and higher. So when Micron says they have 232 layers, they're actually taking advantage of the next piece of technology, which is I can't make a stack this high and drill those holes that accurately all that way. So they're making stacks on top of each other.
Okay.
So they make a stack and they drill all the holes and they make all the connections in some layer of polysilicon, and then they put a insulating layer in and they start the whole thing and build another stack. So that 232 is actually 251 stacks.
Okay.
And that gets around you can only drill holes so straight, well actually etch holes so straight. And as over the next few years, I expect we'll see, we'll go from 232, that's 2 stacks. A couple of weeks after Micron made that announcement, Solidigm announced like 224, so that everybody's playing leapfrog. This generation is there, the next generation may be about 300, and then we'll get to, instead of 2 stacks, it's 4 stacks. We'll go from like 300 to like 400, because the first time we do 4 stacks, they won't be as high, and we'll work our way up, but it's just, the stacking is just how they make flash cheaper nowadays.
So they make flash cheaper. I understand the wafer. The wafer, most of the cost is in the wafer. We build up. Building up is much cheaper than either improving the density of the wafer at a single layer.
Well, we couldn't improve the density anymore. We hit the technical limit.
So
Because if you're going to do QLC flash, that needs 16 voltage levels.
so we
If
become
you only have
super-
16 electrons and one of them gets out, that changed the value.
So I'm following so far. Now what I'm not clear on is what does that translate from a packaging perspective? Am I getting the same sizes? Like when as a consumer of flash, am I getting the same size packages, just cheaper? Or am I getting larger packages?
They're still selling a 1 gigabit chip.
Mm-hmm.
And then 8 of those chips go in the package you see if you open an SSD. But the chips are a little bit smaller, so they get more of them on a wafer,
Right.
so they're cheaper to make.
Okay.
When the density gets to where the 2 gigabit chip will fit in that physical package, they'll switch to 2
So
gigabit.
the PCB, they haven't gotten to the point where a 2 gigabit chip will fit onto the same PCB yet.
It's not the PCB, but when you look at a circuit board, the
Uh-huh.
thing you say is a chip, that
Yes.
package, actually holds multiple chips.
Gotcha.
And when the physical, millimeter by millimeter size of that chip at 2 gigabits fits in that size package with that many legs, which is an industry standard, they'll switch from doing 1 gigabit to 2 gigabit.
And
But
then
doing a
we
1.5 doesn't make any sense.
Exactly. So it essentially at that point, at the 2 gigabit point, that's when we get from 1 terabyte to 2 terabyte, from 4 terabytes to 8 to 16.
Right.
Learned a lot. That's a lot. So bonus question. I talked to Steven about CXL.
Yep.
What does CXL play in all of this, if at all?
So CXL is basically a mechanism for accessing memory over PCIe.
Right.
And what's really attractive about that is it gets us past the limits of the number of memory channels the CPU can provide, so we can have a bigger memory space.
Exactly.
But the exciting part is, since we have PCIe switches and we can use PCIe as a network, we can have shared memory spaces. And so somebody could make a box with 4 terabytes of DRAM in it and 8 PCIe ports that 8 servers can use and all share that memory.
Right.
That's really exciting. But it's memory is memory.
Right.
And flash memory is, well, we call it bit addressable, but it's really 64 byte addressable chunks, because the CPUs read and write 64 bytes at a time.
We put a controller in front of that.
A word line.
Yeah.
But flash is block oriented, like storage.
Right.
And as flash gets denser, the blocks get bigger. So on today's QLC flash, the minimum write size for the chip is 64K.
How much?
64K bytes.
Okay.
So
That's rather large.
Yeah.
When you're talking about bit addressable memory. That's
Right.
like
And-
super inefficient.
And so if you put a controller on it like the SSD guys do, so that you do a 4K write, and it writes 4K to the 64K page and wastes the rest, that's okay for an SSD, because the time it takes for the SSD to garbage collect and fix the waste doesn't really matter. But if you're trying to treat it as memory, and a guy writes 64 bytes, and it takes 64K bytes to hold it, that's going to get weird. So you need kind of DRAM buffering to let you
DRAM
coalesce
buffering
writes,
to
and a management plane. And MemVerge is trying to do that, but I'm excited about CXL, but I remain unconvinced about its expansion beyond the HPC world. Because in the HPC world, guys will go, holy crap, I could have 20 terabytes of memory shared between 8 servers? Great, let me go write code.
and
when you get to the-
they have that level of skill to do that.
That's what they do.
Yeah.
When you get to the corporate world, I think even something like MemVerge, which is a kit to write like a database engine, is too far down, and we need a database engine that does an in-memory database that takes advantage of, something like Aerospike. that fully takes advantage of CXL.
So,
Because that would be, and you talk to it via SQL, and the corporate guys know how to talk to it via SQL, and that would be much faster to get into a corporate data center.
so we've been doing this series, The Future of the Data Center with Micron, and I've painted the architecture picture of this. This is the unsponsored content where we talk about that deep level of technical hurdles, what still needs to be done. While I'm still excited about that picture that I've drawn, this is like the stumbling blocks. This is the stuff that needs to be figured out. Go back and watch the CXL video that I did with Stephen Foskett that talks about the challenges around security, right access control, all these things that need to be figured out, and what Howard just said, which is delivering the value at a higher enough abstraction level where it makes sense for the average corporate data center and not just HPC, which is the promise that I'm telling you that the industry is driving towards. We'll see where we land. Maybe there'll be something in between that the cloud providers take advantage of and not the private data center. We'll see. To learn more about the CTO Advisor, you can follow us on the web, thectoadvisor.com. Thanks Fast Data for loaning me Howard during the busiest part of the show, the last day, to talk about CXL 200 layer plus NAND. Talk to you next year. No, not next year. We'll talk to you at KubeCon in just a few weeks. Until then, see you on the Twitters.